Hello dear students, welcome you all to the next revision lecture of the JCE Connect series of online lecture. In today's lecture, we will discuss one more example on deflection of beams. In the previous lecture, I have discussed with you all the list of formulas, how to apply them. Further, we have discussed two more examples. So let us continue ahead with the third example. So in this example, we have a rectangular beam of cross section 150 by 300 mm, which is supported over a span of 6 meters. It is pre-stressed by a parabolic cable which is at a distance of 120 mm from the soffit at the support section and 60 mm from the soffit at the midspan. Initial pre-stress applied is 300 kN. Determine maximum deflection at transfer stage, central point load which can be applied to nullify the above deflection. Take the density of concrete as 25 and neglect the losses. So this is an example from the question paper. The important task here is to understanding the language and drawing a correct diagram. The question which we have to solve here is, in the first part we have to obtain the deflection at the transfer stage only, and secondly we have to obtain a central point load which can be applied to nullify the above deflection. That means the deflection which we will be getting is going to have a negative value. That means it is an deflection caused by the resisting force or the pre-stressing force which is applied in the initial stages, and the point load we have to determine is such that the deflection which is caused, the point load can nullify it. Nullify it in the sense, the deflection caused by the point load at the workings in the later stages will be nullified by the pre-stress. Actually we mean in this sense, okay, but here we have to find a central point load which is applied to nullify the above deflection. Means it is not that point load is used to nullify the deflection. Already the deflection is there which is caused by the pre-stressing force, which is an resisting deflection. So that resisting deflection can support what amount of point load or what amount of live load we need to find in this example. So here a trick is played by using the language in a confusing way. Locating of the pre-stressing cable also is an important part in this problem. So let's check the figure. So we have drawn a beam of depth 300 mm. So now at the support, okay, the cable is at 120 mm from the soffit. Soffit means bottom of the beam. Okay, so at the support, as we have marked here, the cable is at 120 mm from the soffit, whereas at the center where there is a sagging, the cable is at 60 mm. So first step is understanding the problem, then drawing the diagram correctly. If you make a mistake here, we won't go ahead with the valuation, because once your E1 and E2 values go wrong, valuating your problem doesn't make sense, and if this is a 12-mark example, you might just end up with 2 marks. So let's note down the given data: B, D, L, P, which is the initial pre-stressing force, then C value and ES values. Now E1 is what? The deflection with respect to your edges. So how will we get that? 150 minus 120. So it is 30 mm. Whereas E2 is your midspan deflection, which will obtained by subtracting 120 minus 60, which is 60 mm. So understanding E1 and E2 is very important. Draw the diagram properly, it becomes very easy. So next, let us obtain the dead load, which is very easy. Area of the beam into the density. In this case, density is given as 25, so we are using it. We get the dead load as 1.125 Newton per mm. Next, I value BD cube by 12. These all are the basics. Let us find the EI value, which we can use directly for the calculation. E multiplied by I. Then let us obtain now the deflection caused due to the dead load. formula is well known because already we have solved examples on this. 5 WD L raised to 4 divided by 384 EI. We have all the values with us. We are substituting. So we get delta DL as 1.48 mm. These are all the basic steps and they carry a basic or minimum weightage with respect to marks. Don't feel that you have done 4 steps so you will be getting 6 to 8 marks. No, these are very much basic steps. Now comes the application steps. What we have to do here is we have to obtain the deflection caused due to the pre-stressing force, which is an resisting force. Now here the cable is below your center and then further it is sagging. So we are not getting an direct parabolic shape or a direct rectangular shape of the profile, but we'll get a shape which is a combination of a rectangle and a parabola. Hence in such cases the deflection is obtained by using or applying Mohr's principle. Now again, Mohr's principle is nothing new to you all. You cannot ask the doubt now, how is this? Okay, then again you have to go back to your second and third year of engineering. So we are applying Mohr's principle directly here to find the deflection delta, where we use the formula delta is equal to AX bar divided by EI. So EI value is known. A will be the area of the BMD or the deflected shape, and X bar will be its centroidal distance from either left edge or the right edge. So as I said, the deflected shape can be divided into two parts. One is a rectangle, one is a parabola. So for the rectangle, depth will be P into E1, whereas for the parabola the depth will be P into E1 plus E2, because in parabolic from the center if we take, it is the sum of E1 plus E2, that is the center of the beam. So we calculate the depth of the rectangle and that of the parabola. Now let us apply Mohr's principle to obtain the deflection due to the pre-stress. So as this deflection is a resisting deflection, we are taking a minus sign. So answer will be negative for both the shapes. So firstly, the formula is listed in the previous page. So we have got it here. How we find the area? Area is depth of the rectangle, that is 9 into 10 raised to 6 multiplied by 1/2 we are considering, that is 3000. Total length is 6000 mm or 6 meters into L by 2, that is L by 2 by 2, which comes out to be 1500. So this is nothing but your A into X bar. Okay, X bar is 1500. We are taking only the 1/2 of the portion for analysis divided by EI value which we have found out. Now similarly come to the part of parabola. What is the area of parabola? Again same formula, A into X bar divided by EI. Now these things are again explained in detail during your regular video lectures. So we cannot go much in detail now because these are revision classes. So how we get the area of the parabola? It is 2/3 of the depth into the width. So what is the depth? We have calculated it as P into bracket E1 plus E2, that is 27 into 10 raised to 6 multiplied by 3000 into X bar. So how we find the X bar? This you have learnt in your elements of civil engineering. Okay, 5/8 of 3000. Either we are considering either the left portion or the right hand portion. So from here we want to obtain your X bar distance. So substituting, we get the value of delta P as minus 11.05 mm. So this is the initial deflection which is caused only by the dead load and the pre-stressing force. So as pre-stressing force becomes dominating in this case, we have a negative value, means it is the capacity. Okay, this much deflection it can resist, and now we want to find an equivalent point load which can produce this deflection, so that the end deflection is 0. So maximum deflection at transfer stage will be delta dl plus delta p. We get delta as minus 9.57. So we can put a point load such that that point load has an freedom of causing a deflection up to 9.57. Now this is what is the example which is trickily asked. Similar examples we have done in your RCC also, and I think for your regular paper also one example had come. Find the intensity of the maximum point load which can be placed at the center for a given beam. Okay, so this example is similar to that what we have solved in the RCC, but here we are going by deflection principle. So maximum deflection at transfer stage we have obtained. Then next is what we have to do is to obtain point load which nullifies the above deflection, delta. So what is the deflection caused by a point load placed at the center? WL cube by 48 EI. Delta is equal to WL cube by 48 EI. How much delta we have? 9.57. Now don't take the negative sign here. Negative sign indicates that it is a resisting deflection, that's it. So substitute the values, only unknown will be WL. So you get the answer as 27.26 kilonewton. Now this means that the given pre-stressing which is applied for the given beam can easily resist a live load of 27.26 kilonewton, or in terms of the question asked, how we can conclude a point load of 27.26 kilonewton can nullify the pre-stressing effect or the deflection effect caused in the initial stages. So here we have solved 3 examples. Few more examples are there now which you need to practice. Secondly, again I am requesting you all, don't wait for your friends to come or don't wait for any other thing. Better you start studying. Already your exam forms are filled. No one is coming up with any doubts. That means our classes were very good and you have understood everything. Don't wait for the last moment to ask the doubts. As and when the revision chapter gets over, if you have any doubts, you have to ask them. Don't say that one day I can come and clear all the doubts. This is not a subject in which the doubts can be cleared in one day. Try to be as much as independent as possible. Don't wait for your friends to come down and teach you all, because maintain the social distancing norms. Don't be dependent on combined studies. Go for self-studies, because tomorrow if you join a job, your friend will not come there to help you. Try to be as independent as possible. Solve few more examples. Okay, I think with the end of second module, after the losses topic in the second module, we might give you some working examples also. Who are interested, actually all should be interested, and we expect everyone to solve them. So with this first part I conclude, that is the deflection of beams. Any doubts if you have, you are free to WhatsApp or call between 10 to 4. Avoid coming to college, that's why your classes are not kept in the college. If anything is there which cannot be solved by explanation, then we can think of the other ways. Make the list of the formulas, and from the previous question papers, referring these revision videos, start solving the example. So in the next lecture, we'll start with the most easiest topic, which is losses in pre-stress, which will conclude your module 2 revision. Hope all of you are fit and fine and taking care of yourself. See you all in the next lecture. Thank you.